this a minute, I think. Is this working now? Okay. Maybe I should apologize for the product placement. So today's lecture is a little bit of a mishmash. I wasn't sure exactly what to call it. You'll see why I called it Frobenius actions on de Rham cohomology. But there are several things going on. One thing I'm going to do sort of partway through is explain a little bit more about the comments I made at the end of last time about how to use a Gauss-Amandine connection to compute a Frobenius action on a whole family, on the de Rham cohomology of a whole family of varieties, which you can then use to recover individual zeta functions. But the reason I named the lecture this is because I want to say something which, in fact, will be something that is not completely proved, at least not to my knowledge, about Frobenius actions on de Rham cohomology of varieties, say over QP or QQ, which might not extend smoothly over the corresponding ring of integers. So here's the setting. So if you recall lecture 2, the end of lecture 2 could be rephrased as follows. If you have a smooth proper morphism from X down to ZQ, if you take the generic fiber of this, you get a smooth proper variety over QQ. It has de Rham cohomology. And there was this comparison map between this de Rham cohomology and rigid cohomology of the special fiber. And that gives you a Frobenius action on this thing. So this space, which comes from characteristic 0, sort of naturally inherits a Frobenius action coming from characteristic P. You might then ask the question, well, what if I start with something which does not have good reduction? If you have, say, a curve which does not have good reduction, can you say anything about its relationship, the relationship between the de Rham cohomology of the generic fiber and something made out of the special fiber in some model? And in fact, what happens is you do get something like a Frobenius action on the de Rham cohomology. You actually get something else that goes with it, a so-called monodromy operator. And these things kind of are intertwined. And apparently, these things are compatible with Gauss-Amandine connections. But the apparently is because I have not actually succeeded in finding this written down anywhere. So I'm not going to state this as a formal theorem, but I'll suggest what appears very strongly to be true. In the case, this description will specialize back to the proved statement when you actually have good reduction. And the motivation for where these things come from actually, well, one motivation is purely geometric, sort of. I'll maybe draw this picture a little later. But another source of motivation is what's called p-adic Hodge theory, which at one level can be thought of as the relationship between, say, the de Rham cohomology of a variety over QP and the Étale cohomology of the geometric over QQ bar. So there's sort of a strong relationship between those two things that was sort of the formalism was set out by Fontaine, and then later authors kind of filled in and proved the theorems. I gave a little bit of this in the notes. I decided not to really talk about it in the lecture because it's kind of off the stream of the other things I was talking about, but I'll just mention that there is this motivation coming from a sort of p-adic version, sort of p-adic replacement for ordinary Hodge theory that suggests that you might have these operators even when you don't have good reduction. So now there's this funny thing that happens when you don't have good reduction is that things are not quite canonical. And the way they're not canonical can be most easily described in terms of the p-adic logarithm, which I don't actually remember whether any of those other speakers had discussed this point already. But in any case, so the ordinary logarithm series, log 1 plus x, because the denominators, are the denominator under x to the n is only n, whenever x is in a non-Archimedean field and it has norm less than 1, this series converges. So the logarithm can be defined for anything which has distance strictly less than 1 from 1 itself. If you actually wanted to talk about log on all of, say, QQ, or even its algebraic closure, you have to do something more. So you remind yourself, well, what is the structure of QQ star? Well, you have the units which are congruent of ZQ, which are congruent to 1 mod Q. And then you have the Q minus first roots of unity, which are the Teichmüller lifts of the elements of FQ. And then you have p to the z. Because every element you can, it has a valuation. So if you shift it by p to the z, you get valuation 0. And p, thank you. I should have just stuck with p's. So let me just write that again so that you can read it. So you have the units congruent to 1 mod p, the 1 units. You have the Teichmüller elements, and you have p to the z. So this lets you fix up the valuation. This lets you fix up the element of the residue field, and this is what's left. And the log series converges on here, on these terms. And these terms, well, what do you want? You want the log to be a homomorphism from the multiplicative group to the additive group. So you want log of a product to be the sum of the logs. So that suggests that you had better set the logs of roots of unity to be 0. But then there's an ambiguity as to how to set log p. So you have to make some choice at this point. You have to choose the value of log for some. If you choose the value of log for any one element of QQ or even QQ bar, which has norm not equal to 1, that fixes everything else. And the resulting function is called a branch of the p-adic logarithm. This is somehow thought to be analogous to choosing a branch for the ordinary logarithm in the complex plane. So you could, for instance, just take log of p equals 0, but there's nothing particularly distinguished about that choice. So I'm going to leave the choice in, leave the ambiguity in, and you'll see later how it arises. So you'll also see that the contribution of the p-adic logarithm actually drops out when you're looking at good reduction. So there will be a failure of canonicality that does not appear in the good reduction case. Okay, so we had the notion of a semi-stable curve in the previous talk. So I mentioned the higher dimensional version, although my examples will always be curves. You have a proper flat morphism, and I'm only going to do this over a one-dimensional base, like ZP or ZQ. I'll say that pi is semi-stable if it's smooth over sort of most of the points, and for whatever points are left, the fiber is a reduced normal crossing divisor. So for a curve, this is, as Matt said, you want the fiber to be reduced, and each sort of component, each component should look, maybe it should only cross other components or maybe itself at double points. I guess when I mentioned this before, I didn't allow self-crossings, but I want to have this example, which has a self-crossing. So if you look at the Legendre family of elliptic curves, and you pick out a curve, x minus 1, x minus lambda, so for this to be smooth, okay, this is not quite correct. Let me write the correct statement. Okay, so x minus 1, x minus lambda over zq is smooth. So this is smooth, y squared equals, if and only if the valuation of lambda and lambda minus 1 are both 0. So, no? Sorry? Oh, yes, p is not 2 or 3. P is not 2 or 3. Thank you. So this model, yeah, so this curve, if you avoid 0 or 1, if you avoid reducing to 0 or 1, you actually get a smooth curve. So I need the big marker over the computer screen. But to get semi-stable, let's say semi-stable and not smooth, then that happens if, say, VP of lambda is 1 or VP of lambda minus 1 is 1. Right? Because essentially what's supposed to happen is you want the, there are sort of two branches. Right, let me write this down. Let's say lambda is congruent to 0 mod p. So then this reduces to y squared equals x squared x minus 1, which is singular, mod p. But mod p squared, you can separate the branches. So, and likewise if you're close to 1, but not too close. I'll mention in passing, because this will be relevant later, of course, this curve has a Tate uniformization whenever lambda is, say, for, okay, this again, you have to put lambda or lambda minus 1. If lambda, say, let's say if, okay, pretend this is a big fat marker. If lambda has positive valuation, then you can parameterize this as a quotient of the quotient of C star, which will be relevant a little later. Okay. To p squared, if lambda is p squared, because I think the fiber is, let's see, what's wrong? Is the fiber not reduced? Or? Oh, yeah, my normal crossing gets screwed up. Yeah, because something is not right here. Right. Oh, sorry. I need to assume that the total space is regular. Okay. Why don't I just try writing this out on here, and then just ignore this slide. Okay. So pi x over s is proper flat. Pi semi-stable. What? I want x to be regular. I want pi is smooth. So dimension of s is 1, let's say. Smooth over s minus finitely many points, let's say. Closed points. And the fibers are reduced with normal crossings. So, in fact, I could get away with somewhat less than semi-stable in what I'm going to talk about. But for simplicity, let me just assume that. OK. Moving on. So, yeah, and so in particular, on this slide, I could get away with somewhat less. But let me just say it this way. So you say you have a semi-stable morphism. So what happens is that the de Rham cohomology of the generic fiber now has not one but two natural operations that come from characteristic P. There's Frobenius, which is semi-linear for the P. There's a Frobenius map on this thing, which is congruent to P powering mod P. And Frobenius is semi-linear for that. And there's the second order operator monodromy, which is actually linear. It's nilpotent, which follows from this commutation relation between the two things, that n phi is p phi n. In the smooth case, this n will vanish. And under certain circumstances, you could actually prove a converse, but let me not try to state that. Let me just say that, yeah, if you have a smooth morphism, then you don't see this n. And in particular, it certainly satisfies this condition. But in general, you do see an n, and it actually imposes some sort of restriction on the Frobenius. Now, as I said, things are not completely canonical. There's a dependence on branch of the p-adic logarithm in the phi, but not in the n. And the reason is because if you change the branch, you'll actually see this sort of in action a little later. But when you change the branch, you end up conjugating phi by something like an exponential of c times n. Remember, n is nilpotent, so exponentiating a nilpotent operator means just writing out the exponential series, and it stops after finitely many terms. So also notice that if you conjugate n by this, it doesn't change because n commutes with any power series in n. So, so when you change the branch, you conjugate everything by this expression, but that only affects phi. It doesn't actually affect n. Okay, so, and where does this come from? So it was, as I said, this was proved by Kyoto and Kato following sort of suggestions by Fontaine and Janssen, maybe some other people. The reason this exists, this is not quite the interpretation that Kyoto Kato originally gave, but this is this interpretation. I know I found this in a paper by Elmar Grosseklin. I don't know if it's original to him, but essentially there is a comparison theorem, just like in the good reduction case. There's a comparison theorem that explains this, but there's a wrinkle. So the comparison theorem says, okay, so there is a comparison isomorphism between this de Rham cohomology of the generic fiber and something associated to this special fiber. So this x bar now has to be thought of as a logarithmic scheme, which I don't want to get into the details of what that means, but given the shape of x, it has reduced normal crossings. There's sort of a natural way to view it as a log scheme. And there is then a sort of analog of rigid cohomology where, I'll come back to where it comes from in a minute, but there's an analog of rigid cohomology for this log scheme in characteristic P, and it carries a Frobenius operator and a monodromy operator, and that's where these things come from. They get transferred over. Now, what's different is that the comparison theorem in the good reduction case was the map was more or less obvious once you set things up right. You said, well, okay, X is this smooth proper thing over ZQ, so its generic fiber sort of naturally can be turned into an analytic space, and that process of analytification actually just gave you the comparison map. That's not what's going on here. And the reason it's not what's going on here is because if you have something in characteristic P, which looks, say, like this, and you want to compute this Kyoto-Kato cohomology, this sort of logarithmic version of rigid cohomology, what you do is, again, you make sort of, locally, you restrict to affines, you take an affine, you lift to characteristic 0, and you sort of construct the analogous thing. But what you're doing is you're not constructing a smooth lift. You're constructing a lift that looks basically the same as the thing you had before. In particular, if you have these two components crossing, the lift you construct in characteristic 0 will also have two components crossing. So you don't actually construct the space you're not constructing is not really this, or a sort of analytic version of this. You're constructing something else, and the comparison map somehow, to get the comparison map, you have to somehow deform this thing into the cohomology of some sort of log scheme, which is a lift of the thing in characteristic P with the same sort of singularity. So there's something a little more mysterious about how this map is constructed, and in particular that process, there is some sort of non-canonicality built in. There's some sort of dependence on a p-adic logarithm branch. So this looked a lot like the arrow I had in lecture 2, but really it's much subtler in terms of the way it's originally constructed. The goal of the talk is to at least make a proposal that says that maybe this is not so subtle. But again, this is not something that whose proof actually appears in the literature, although it should be. So one comment I will make is that this actually is reasonably easy to compute in a particular situation if X admits a p-adic uniformization. So this concept of a p-adic uniformization occurred in Jeremy's talks. And so you can write down what this is sort of explicitly. For instance, if you have a Tate elliptic curve, if you have one of these parametrizations of X as a quotient of the multiplicative group, which only works if X has split multiplicative reduction, then you could do something like this. Construct this. You could construct the operators at least. You can construct the map too. So there are various names of people who have worked on this. But yeah, the main thing to take away from this slide is that there's something a little bit mysterious that one would like to fix. So what I want to propose in the rest of the talk is how a recipe that, as I said, appears to reconstruct this mysterious structure of the Frobenius and von Neumann operators using the principle that I introduced in the third lecture, that Frobenius somehow behaves nicely with respect to a Gauss-Monning connection when you have a family of varieties. So to keep things simple, I'm going to set notation a little more restrictively than I did before. So I'm only going to allow the base to be basically a subset of the affine line. So take an open dense subscript of the affine line. Well, I guess I didn't have to say dense because it has a point. It should contain t equals 0. So you can throw out some things, but don't throw out anything congruent to 0. So what do I want now? I want a proper flat morphism, and then I want it to be. So here's the picture I want. Here's the picture I want. So here's S. S might be missing some. Here's SQP anyway, the generic fiber. And inside this, there is so sort of you can think of this as a rigid analytic space, and there's a slightly smaller analytic space consisting of the analytification of the completion of S hat. So this thing this thing misses some residue disks in the affine line, whereas this thing only misses finitely many points. Let me draw it up. So this is S hat n is the complement of finitely many open unit disks. But in particular, the disk around t equals 0 is not taken out. So t equals 0 is here, and there's a disk around it. And I want this thing to be. And so now I have x sitting over this, maybe xqp sitting over this, some family of curves. And so what I want to have happen is that there is possibly a singular fiber over t equals 0, but no other singular fibers on Sn. Maybe there are some singular fibers over the other disks, but on S hat n, I only want there to be one singular fiber, and I want it to be over this particular point, t equals 0. So for instance, if I'm looking at the family of Legendre elliptic curves, which is somehow my favorite example in this lecture series, let's see, I should maybe invert lambda equals 1 so I don't get into the same trouble that I got a couple of slides ago. But I definitely do not want to invert lambda because I want to keep lambda equals 0 in as a singular fiber. Right? This thing over the affine lambda line, the only singular fibers are lambda equals 0, lambda equals 1. So as long as I don't have lambda equals 1 knocking around in here, the only bad fiber is lambda equals 0. Okay. So if I take out, so over SQP, and as I said, so most of these fibers are smooth. There are some finite number of them that are singular, and if you take those out, you have some space T. So that's an open. So that's a QQ scheme. So you have a vector bundle with a connection on. So away from these bad points. So this is a bad point, and there may be some other bad points out here. Away from those, you have a vector bundle with a connection from the previous lecture. It's the Gauss-Manin connection. And it makes sense whenever the fiber is smooth, say smooth and proper. But now I want to say that, well, because I have a semi-stable morphism, I can actually do a little bit better than that, that actually something sensible happens even over these bad points. So what happens is that you actually get a sensible vector bundle on those bad fiber, even over those bad fibers. The only difference is that the connection is the so-called logarithmic connection with nilpotent residues. What that means, in sort of explicit terms, is that, let me say what happens in a neighborhood of 0, because that's the point I'm interested in. So you don't necessarily get an action of the differential operator ddt, but you do get an action of t times ddt, because somehow what the connection can do is it can take this thing to some combination of things like some function, section, tensor, not dt anymore, but you can have a dt over t. So if you just allowed d by dt to act, you would get some singularities. But if you multiply by t, then you're okay. Of course, this only works at 0. If I was looking at some lambda, I would have to multiply by t minus lambda instead. So in a neighborhood of 0, this is okay. This might be bad at the other singular points, but never mind. Of course, if you actually have no singular fiber at 0, then, I mean, ddt already acts, so t ddt already acts. The one other thing I should mention is that, so I made this comment about nilpotent residues. What does that mean? What that means is that, I think I have this written out on the next slide. I have this written out on the next slide, so I will say it then. And if you think back to lecture 3, lecture 3 said if you didn't have any singular fibers, then you would, on S hat n, you would get a global Frobenius action. So if in particular, if I took out this disk, this open disk containing t equals 0, then I get one of these Frobenius actions on what's left. So on S hat n minus the disk around 0 of radius 1, which is, what are we using to say the open disk? A minus superscript? Great. I think that's consistent with what everybody else was doing. On this thing, you get a global Frobenius action, which you could, I originally wrote it down as some sort of isomorphism between, so I say E is the vector bundle I'm talking about. So if you take any Frobenius lift, say it acts on S hat n, so mod p, it should be the, let's say, q power Frobenius, then on S hat n away from this disk, you get this isomorphism of modules with connection between E and its Frobenius pullback, which you can think of as a semi-linear action of phi, which has this compatibility with the connection. And what turns out to happen is that this always extends to some space of the form S hat n minus d0 1 minus epsilon. So you always get an action. So the picture is scrolled off. So in this picture, this open dash boundary is at radius 1. What I'm saying is that the Frobenius action, which sort of originally only made sense on here, actually persists a little bit into the disk, like 1 minus a bazillion. So that has extremely important consequences, just that little bit. I mean, essentially, it comes down to the fact that this complement of this open disk, together with the open disk, does not make an admissible cover of S hat n. But if you get in a little bit, just any little bit like that, this plus the open disk is an admissible cover. So that's somehow the relevance of this property, that you get the Frobenius persists a little bit into the disk where it doesn't really have a right to be defined. OK. So now let me say a little bit of this in terms of more explicit terms. OK, so let me let D be D0 1 minus, the open unit disk around T equals 0 in S hat n, and say I write down a basis of sections, which in fact is always possible, but we don't need to justify that right now, just for the sake of explaining an example. So the action of T by T times d dt, as I said, is somewhat sensible if you ignore an extra parenthesis. So how does this work? So it's basically the Leibniz rule. You differentiate the coefficients, and then you differentiate the s's, and there's some matrix that keeps track of how to differentiate the s's. It's the same thing that I wrote down in lecture 3, except it's multiplied. Now it's the action of T ddt instead of d dt. So there's some matrix n that has this property, that you multiply this column vector by n, and then you also differentiate the column vector, and that's how you compute the action of differentiation. And what this nilpotent residues condition means is that this matrix n, which is a power series in T, its constant term is a nilpotent matrix. In the case of good reduction, where you didn't have a logarithmic singularity, this n0 would be 0, because you could have just written down a matrix corresponding to the action of d dt and then just multiplied it by t. So then it wouldn't have a constant term. But if you have one of these singularities, this n0 actually will have a constant term. And one is recommended to try this for oneself, say, for the Legendre family, which is, in fact, something that my project group has been doing, sort of expand these things out and see what they look like. So you can now ask the question, well, how do I sort of solve this differential equation? Well, here's a first approximation of how you solve it. There's a unique matrix of power series, starting with the identity matrix, such that so this thing that I've written down here is the effect of changing basis by u. So if you replace these c's by sort of the new basis specified by u, you change this matrix n by replacing it by u conjugate, but then you have to also differentiate the change of basis matrix. So what you want to have happen is you want to change things in such a way that you get the constant term and then no other terms. Notice if you have u congruent to I mod t, you're not going to change the constant term, because this is not going to change the constant term, because mod t you're conjugating by the identity matrix. Mod t, this is multiplication by the identity matrix, and this is 0 mod t. So you can't change the n0. You don't hope to get rid of the n0, but you hope to get rid of everything else. And so this specifies a basis of formal sections on which this operator acts just by this residue map. So this is an interesting exercise that I think is in the problem as an exercise in the project section. I think at this point, yeah, my group has solved this because so now there's a funny thing that happens here. Actually, there's a funny thing that happens more generally with p-adic differential equations, which you won't notice right away until I show it to you. So you might ask, well, does this matrix converge on D? Because it's sort of a solution. It's a solution of some sort of differential equation. You can think of this as a differential. If you move U to the other side, this is a differential equation on the entries of U. You can ask whether this equation has a solution which converges on the whole disk. And in fact, it does in this case, but it's not trivial. It's because of that Frobenius action that persisted into the disk a little bit, and an argument that goes back to Dwork. And the main point I want to make here is that the statement I just made is actually a non-trivial property of n. It isn't, if you just write down a random matrix n with entries convergent on the unit disk, you will not get a solution on the whole unit disk. And here's sort of typical example. In fact, sort of the simplest example you can possibly imagine works. Let's say the action of, I don't even need a log for this. Say the action of d by dt on a single section is just to fix that section. So essentially, I'm writing down the differential equation y prime equals y, or maybe minus y. So this thing has a horizontal section, which is s times, I think, the exponential of minus t, which is, of course, s times the power series 1 minus t plus t squared over 2 minus t cubed over 3 factorial, so on. And this only converges if absolute value of t is less than the absolute value of p to the, what is it, 1 over p minus 1? I think that's right, 1 over p minus 1. So, of course, this is not a condition. This isn't too much of a condition if you're taking elements of QP, except maybe if p is 2. But it's certainly a condition over ramified extensions. And rigid analytically, it's a real condition. Yeah, so this differential equation actually makes sense on the entire affine line, but the solution does not live over the entire line. So, in other words, the fundamental theorem of ordinary differential equations is not true over the p-adics. It's just completely false. This is somehow the source of a lot of difficulty when working with p-adic analysis, but in the presence of a Frobenius action, things get fixed up. This is a principle that persists through much of Dwork's work and subsequent. And it applies basically whenever you construct a Gauss-Manin connection, you get some sort of Frobenius action on it, and so you get good solutions of differential equations. But of course, this is not really, so I called this slide parallel transport, but that's a bit of a lie. Parallel transport would mean you actually have a basis of horizontal sections, and you can use those to identify different fibers. These are the column vectors in U are not horizontal sections because this is not 0. If this was 0, then the column vectors of U would actually give you horizontal sections. So how do you fix that? Well, you bring in the p-adic logarithm. Oh, actually, I'm not going to fix that yet. So you're going to fix it by bringing in the p-adic logarithm. But before I fix that, let me point out that if you don't have a singularity, then I can say something sensible. And this is sort of follow-up to the end of my talk yesterday. So I made this comment at the end of my talk yesterday that, OK, so if you have some smooth family, and you know the Frobenius matrix on one fiber, you can use the connection to find the Frobenius matrices on the other fibers. Here's how you do it. so here n0 equals 0. That means that U actually does sort of specify a trivialization of this vector bundle on this disk. So now what I'm going to do is, so I'm going to assume that 0 is the fiber for which I know the action on de Rham cohomology. So what I want is I want my Frobenius lift to actually fix t equals 0. So for instance, if it just sends t to the q, that would work. But you could do something slightly more general. In any case, yeah, so I want t equals 0 to be fixed. So if t equals 0 is fixed, so I can write down the global Frobenius action in terms of the matrix A, which is u times A0 times phi of u inverse, where A0 is the Frobenius action on here. So what you do, and so for instance, Ralph Gerkman has carried this out in some examples, and several other people have carried this out. We're experimenting with an example or two in my project. So you start with some A0 where you can write down the Frobenius action. So for instance, you might take a family of elliptic curves and take the one in the middle to have complex multiplication. So then you can use the extra endomorphisms to detect what the Frobenius action is. So you can write down A0, and then you write down this matrix U by solving the Gauss-Manin connection. Then you write down this matrix A. This only gives you a power series on the disk, but you know in advance that this power series is supposed to be the expansion of some rigid analytic function, which is defined on S hat n, maybe even on some strict neighborhood of S hat n. And so you do something like you can think of it as analogous to sort of rational reconstruction from a power series, sort of recognizing a power series as a rational function. You do something like this to recognize the rigid analytic function that you have, at least approximately, p-adically approximately, as having this power series expansion. Again, the power series expansion is also truncated, but so you have to keep track of how many terms of all the, in p and t and so on that you need to get accurate results. But just conceptually, what you do is you take this power series in the open unit disk and you recognize it as the expansion of some rational function. That rational function you can then specialize at a point in another disk. But it better be a point that is fixed by phi. But you specialize to a point in another disk to get the Frobenius action there. So that paradigm actually, people have actually executed this in some examples, and it really does work. From the point of view of this talk, I want to discuss the question, what happens if you want the Frobenius action on some point which is not t equals 0? If you want the Frobenius action, maybe I should have written t not equal to 0 here. If you want the Frobenius action on the other points, see, the problem with what you're doing here is you're really relating, remember that Frobenius written as an isomorphism between phi upper star of the bundle and the bundle, that's giving you an isomorphism between a point and the fiber over a point and the fiber over its image under phi. So if the point on the base is not fixed by phi, it's not telling you anything useful. So if you actually want something that tells you the Frobenius action at all of the points, what you just do is you write down u times a naught times u inverse. So in other words, you use u for parallel transport to get from your point in your disk to the origin. You perform the Frobenius action at the origin, which is A0, and then you parallel transport back. This, unfortunately, does not extend outside the disk, which is why this thing is interesting. This thing actually lives globally. This does not, but this is what you need if you happen to have the action on de Rham cohomology of x0 and you want it on xt, where t is close to 0 but not equal to 0. And the reason I mention this is because this is a better description of what one has to do when there's a singularity. So if there's a singularity, here's what you do. So here you bring in the p-adic logarithm. So now you adjoin a formal symbol log t, which behaves as you expect log t to behave. So for instance, the differential of log t should be dt over t. Right, so I prescribe d of log t to be dt over t. And now I also have to make some restriction on phi so that I can extend the action of Frobenius. So I'm assuming that Frobenius, so phi of t over t to the q minus 1 has norm less than 1 on d. So for instance, you could certainly take phi of t equals t to the q, but you could also take, for instance, t to the q plus p. That would also work. Is that right? I think that would work. Yeah, because basically I want to be able to define phi of log t like this. But I want this to be an actual power series. Let's just say phi of t is t to the q for simplicity. So then this really is, then I should just write phi of log t as q log t. Okay, so then what happens is the global Frobenius can be written this way: u tilde a0 phi of u tilde inverse for some constant matrix a0. This a0 is supposed to be the action of Frobenius on the singular fiber. So it's something. Let's not worry about how to actually get it, but let's say there's some matrix A0 with this property. And since A was global and didn't actually involve log t at all, you can sort of mod out by log t, and you get this expression for it, u A0 phi u inverse. But this isn't what we want, because this doesn't tell me about fibers other than t equals 0, which is a singular fiber. So that's not what I want. So what I want is the analog of this expression, which is the same thing, and now I have to use u tilde. And now the point is that this thing actually has log terms running around in it. If you actually write this down, this has logs all over the place. So it actually depends. So you have to pick a branch of the p-adic logarithm, and only then you can evaluate this. So if you choose a branch of the p-adic log, you can actually evaluate this expression because you can plug in for log t. And the claim, so one of the things my project has been doing is looking at trying to experimentally verify this in some simple examples using a Tate parameterization to see that this actually computes the Frobenius action. So strictly speaking, I didn't tell you that there was a Frobenius action when xt didn't have semi-stable reduction, but in fact, there is a more general definition that allows Frobenius actions. Say whenever t has absolute value less than 1 or say lambda has absolute value less than 1 in the Legendre family. But if lambda has valuation equal to 1, then that actually is a semi-stable thing, and so this is a testable hypothesis. And there's a related statement about monodromy. So as I said, this was obtained by parallel transport from the fiber t equals 0. You should do the same thing for the action of monodromy. So you parallel transport n0. This turns out to be the same as without the tildes. So this is a reflection of the fact that the monodromy doesn't actually depend on the choice of the p-adic log, because when you compute this expression, the logs drop out. This you can also rewrite like this, because that was from the definition of u, right? The definition of u was supposed to solve this equation here, so you could just rewrite this. But that doesn't matter. The point is that you have some expression in terms of u and another matrix n0, which again, maybe you don't know what it is a priori, but if you take two different values of t, you could compare the predicted values of n0 and see if they agree. And so the proposal is that this computes the monodromy action. So there are various ways one could test this. I'll just conclude by mentioning some of these. One is to, as I said, take an example like the Legendre family where you can look at curves that have a p-adic uniformization. And in those cases, you have another recipe for computing the Frobenius actions and the monodromy. And you can compare, even if you don't know the values of A0 and N0, you can compute them twice by solving for them from values for non-zero t's, you get two different predictions for A0 and N0, see if they're the same. You can also check whether this Frobenius action satisfies some sort of analog of the Weil conjectures. So in usual rigid cohomology, the eigenvalues of Frobenius are supposed to be algebraic numbers with absolute value q to the I over 2 if you're looking at hi. That's Deligne's theorem for L-adic cohomology sort of transferred over into p-adic cohomology. It still remains true. In this situation, you don't expect the Frobenius action to have eigenvalues whose norm is q to the I over 2 necessarily, but you get some concrete prediction about them. Essentially, what you do is you make a filtration out of the monodromy operator called the Jacobson-Morozov filtration. And on the sort of pieces for that filtration, Frobenius acts with certain type of eigenvalues. You can actually check that numerically for something that you compute. Well, for this, you have to actually give a recipe for computing A0 and N0, but one can actually, I guess one can extract A0 from this expression and then plug it back in to this expression to get what you're supposed to see for non-zero values of t. And you can test this as well. Not that this test hasn't actually been carried out yet, but so some progress towards making some of these tests has been happening in the project group, and depending on how much progress we make during the rest of the time, some of that may get reported on. So I guess that's where I should stop. Thank you. Hey.
So remember, at a stage, you mentioned something unsolved at the end of